Okay, so now to talk about inference for experiments. So in an experiment, researchers usually hope to see a difference in the responses so large that it's unlikely to have just happened because of chance. So we can use the laws of probability, which describe chance behavior, to learn whether the treatment effects are larger than um, we would expect to see if only chance were operating. If they are, we're going to call them statistically significant. So if we observe statistically significant differences among the groups in a randomized comparative experiment, we have good evidence that the treatments cause these differences. You will often see the phrase statistically significant in published research reports in many fields. The great advantage of randomized comparative experiments is that they can produce data that give good evidence of a cause and effect relationship between the explanatory and response variables. So we know that in general, a strong association does not imply causation, but a statistically significant association in data from a well-designed experiment, it actually does imply causation. This is an activity that we're actually going to do in class, but not now. Okay, so a completely randomized designs that are the simplest statistical designs for experiments. But just as with sampling, there are times when the simplest method doesn't yield the most precise results. So this would be an example of when a completely randomized design would need some modifications. So suppose that a mobile phone company is considering two different keyboard types, design A and design B, for its new smartphone. The company decides to perform an experiment to compare the two keyboards using a group of 10 volunteers. The response variable is typing speed, measured in words per minute. How should the company deal with the fact that 4 of the volunteers already use smartphones, where the remaining 6 do not? They could use a completely randomized design and hope that random assignment distributes the smartphone users and non-smartphone users about evenly between the two groups using keyboard A and the groups using keyboard B. Even so, there still may be a lot of variability in typing speed in both groups because some members of each group are much more familiar with smartphones than others. The additional variability might make it difficult to detect a difference in the effectiveness of the two keyboards. So what should researchers do? Well, what they should do is they should block. So because the company knows that the experience with the smartphones will affect typing speed, they could start by separating the volunteers into two groups, one with the experience and one without the experience. Each of these groups will be called a block. So a block has similar subjects within them. So it's kind of like strata if you think about it. So they're similar within. Within each block, the company could then randomly assign half of the subjects to use keyboard A and then the other half to keyboard B. To control other variables, each subject should be given the same passage to type while in a quiet room with no distractions. So this would be called a completely randomized block design, which helps account for the variation in the typing speed that is due to the experience with smartphones. So it would look something like this. So you have your smartphone users separated from your non-smartphone users. Those are your blocks. Think of it, it's just like strata. Then you randomly assign to keyboard A and keyboard B in both groups. You compare the speed within both groups, and then you compare the speed among the different blocks. So a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect uh, the response of the treatments. In a randomized block design, the random assignment of experimental units to treatments is carried out separately within each block. So form blocks based on the most important unavoidable sources of variability. So they're lurking variables among the experimental units. These are things that you usually can't control. So gender would be a good thing to block in certain situations. Okay, you can't control gender. You can't control height. You can't control weight. You can't control age. Okay, so those are things that, because you can't put a control on them, you may want to block those things. So randomization will average out the effects of the remaining lurking variables. So in the last one, noise or passage that they had to type, and allow an unbiased comparison of the treatments. So just kind of like an experimental mantra that we have to kind of follow always is that we control what we can, and what we can't we'll block, and then we randomize to create comparable groups. So control what you can, you block what you can't. Randomization will take care of the rest of the lurking variables that can affect your results. So going back to the keyboard problem. So using a randomized block design allows us to account for the variation in the response that's due to the blocking variable. So it makes it easier to determine if one treatment really is more effective than the other. So to see how blocking helps, let's look at the results of an experiment using the 10 volunteers, 4 who already had smartphone use and 6 that didn't. The 4 smartphone users, 2 of them used A, 2 of them used B, and then with the non-smartphone users, 3 were on keyboard A and 3 on keyboard B. Each of the 10 volunteers will type the same passage, and the recording speed is the typing speed is recorded in this dot plot. So there's definitely some evidence that keyboard A results in higher typing speeds, but the evidence is not that convincing. Enough overlap occurs in the two distributions that the differences might simply be to the chance variation in the random assignment. So if we compare the results for the 2 keyboards within each block, however, you get a different story. So among the 4 smartphone users indicated by the blue squares, keyboard A was a clear winner. Likewise, among the 6 non-smartphone users indicated by the gray dots, keyboard A was also a clear winner. So the overlap in the first set of dot plots was due almost entirely to the variation in smartphone experience. Smartphone users were generally faster than non-smartphone users, regardless of the keyboard they used. But then when you actually highlighted them, you can now see that keyboard A was faster among non-smartphone users as well, and so that would be the clear winner. Okay, so just a quick example, and we'll be done with this video. So women and men respond differently to advertising. Researchers would like to design an experiment to compare the effectiveness of 3 advertisements for the same product. So we're going to explain why a randomized block design might be preferred to a completely randomized design for this experiment. A completely randomized design considers all subjects, both men and women. In a random assignment, would send subjects to 3 groups without regard to the gender. So a random block design will consider men and women separately. Random assignment will occur in each block. Blocking will account for the variability in responses that are due to gender. Now let's outline a randomized block design using 300 volunteers, 180 men, and 120 women as subjects. And then we'll describe how we would carry out the random assignment required by your design. So we have the 300 volunteers. We're separating them to the 120 women, the 180 men. We'll randomly assign the 120 women to 3 groups, 40 in each. Each group will see a different treatment. And likewise with the men, distribute the 180 randomly among 3 groups. Each group will see a different treatment. First, compare results within each block, and then compare between the blocks. Okay. This will actually be the end of it. So a common type of randomized block design for comparing 2 treatments is a matched pairs design. So the idea is to create blocks by matching pairs of similar experimental units. So a matched pairs design is a randomized block experiment. It's just like a twist on it. So they match similar experimental units. So sometimes a pair in a matched pairs design consists of a single unit that will actually just receive both treatments. So since the order of the treatments can influence the response chances used to determine which treatment is applied first for each unit. So if you think about like blocking, right? So blocking, I might separate females and males, okay? Because I suspect that they may respond differently. So if I have 50 evenly mixed males and females, blocking them would be separating 25 males to 25 females, and then within the 25 females, I'm going to randomly assign 12 of them to treatment A, 13 of them to treatment B. Likewise with the males, I'll randomly assign 12 to treatment A, 13 to treatment B. A matched pairs design would be a little bit different. So there's kind of 2 ways to look at it. The first way could be that you separate them, so you'd have probably less, though. You don't usually do a matched pairs design with a larger number, but you could. So let's say I had 10 females and males, 5 of each, right? Then I'm going to separate them to 5 female and 5 male. And now within the 5 females, I'm going to have everybody first do treatment A, then everybody do treatment B. Or I'll randomly assign, but everybody will do treatment A and treatment B. And then likewise would be with the men. I'll randomly assign a treatment first, so they'll first start with B, and then they'll move on to treatment A. But every one of the 5 are doing both. Okay, that's it with this. Yep, that's it with this video. One more video and then we're done.